And now, everyone, our keynote speaker. We're honored to have with us today Dr. Darren Williams. Dr. Williams is a professor of astronomy and astrophysics and planetary science at the Penn State Behrend campus in Erie, Pennsylvania. He also studies the climates, orbits, observational characteristics, and dynamical evolution of planets and satellites. His keynote presentation today concludes this year's Black Forest Star Party, and his speech today looks like I have my pages out of order, so we'll let Dr. Williams take it over from right here. Dr. Williams, welcome.
Okay, I'm happy to be back in Cherry Springs at the Black Forest Star Party. First, a shout out to our previous speakers. They were outstanding. One second. So our previous speakers, if you were here, did a remarkable job. I'm happy to see science shared with the public whenever possible in any form. So that was great. And for me, this is a perfect time to give this talk because I've been working on this topic for many years. It seems like my whole career. And this is really a culmination of a career of curiosity about the Earth and Moon and about the way the Moon formed. And I'm excited to share these results because there's just about to be some press about these specific results because it represents a new way to think about how the Moon may have formed. No one knows how the Moon formed, including myself, but I'm adding to the list of possibilities for how it formed. And so I'm excited to share this with you today. And so we'll start out with this image here. The script of Avatar was written in the mid-90s by James Cameron at about the same time that I wrote a paper as a graduate student about the prospects for giant moons around extrasolar planets like Pandora around Polyphemus, this gas giant planet. I didn't talk to Cameron when I was writing that paper, but it was about the same time. And then years later, I wrote this paper about the possibility of forming these giant Earth-sized moons by capture around gas giant planets, and it made the cover of Astrobiology magazine. I don't think they actually have hard copies of magazines anymore. It's all web-based stuff, but that's an image that I made in which I'm imagining that the thing that is captured comes in as a binary, and the binary has a close encounter. It's going around like this, and it has a close encounter with a gas giant planet. In this case, it looks like a lot like Neptune. And then the giant planet then rips it apart tidally, and one object is captured, the other one is let go. This is called in astrophysics now. Well, I learned it myself. It's a binary exchange encounter, and this is what you see if you were looking down on it. You'd see at the bottom of the screen, there's two lines, a blue and a red one. That's the binary coming in, circling around. And then when it has a close encounter with the planet tidally rips it apart, and one of the objects ends up in orbit. But notice that orbit. Keep that in mind, that shape of that orbit. That's not the Moon's orbit today, right? So there has to be some other part of the story. So one of the objects gets captured as a moon, and the other one can get let go like this. And that paper in 2013 was based on this paper, which I didn't publish. This was 2006, I think, in which it was suggested that Triton around Neptune was formed in this way. Maybe it belonged to a binary, and maybe the member that got lost might have been the size of Pluto. All right, so if you want to be brave about it, you could say Triton was captured in a retrograde orbit it actually goes around Neptune in a clockwise sense, whereas Neptune goes around the sun in a counterclockwise sense. And so we call that a retrograde orbit, and it's a very peculiar property. There are other moons in the solar system that do this, but not big ones. Triton is just very unusual. It's going around backwards relative to the direction that Neptune goes around the sun. So the explanation advanced in this paper, 2006, which I found inviting and interesting, the binary exchange encounter reaction, in which you have a binary produced somehow, maybe through collision, and then the binary has a close encounter with the planet, and then maybe Triton was captured this way. So here's the paper by Agnor and Hamilton. Triton is shown. There's a lot of objects way in the back of the room. You can't read this, but the big moons you've already been introduced to today: Io, Europa, Ganymede, and Callisto. Those are the Galilean moons of Jupiter. And then if we go pan over here, we have Neptune. Triton is a big moon going retrograde around Neptune. There are other moons of Neptune, many moons of Neptune. Saturn has this one big one, Titan, and then a lot of little ones. And Earth, as you can see here, has a huge one. And so you can make big moons not just around giant planets, but around terrestrial planets. And I gave the astronomical community, to be fair, I gave them a long time to read my 2013 paper and to then take that result and apply it to the terrestrial planets in the solar system. And no one did. Either they weren't paying attention or they didn't think it was worth doing. So a few years ago I said to a colleague we have to do this calculation. We have to see if you can form big moons around terrestrial planets, just like giant planets. And I did the calculations, and lo and behold, I'll show you some of those in a moment. And you can capture big things around an Earth-sized object. In fact, you can make a Mercury-sized or a Mars-sized moon around the Earth just by a collisionless capture called a binary exchange encounter. So a little bit of first information about the moon and how peculiar and freakish it is. Right? It exists in this table, the largest solid worlds in the solar system. You see the moons of Jupiter, Ganymede, Callisto, Io. Titan around Saturn is shown there, and you can see the Earth masses. Keep that in mind for what follows, because Mars is 1/10 of an Earth mass. The moon is 1/81th of an Earth mass, or you can think of 1%. So if somebody asks you on the sidewalk or tonight in the dark, how big is the moon? It's 1% of an Earth mass, roughly. Bigger than Europa, Triton, and Pluto. Right? So there is the moon compared to the Earth in size, and so a softball on this scale, you see the globe here. If you want to do distance to scale, I'd have to go out to the side here, maybe where that gentleman is standing, or where that gentleman is standing. That's about 30 Earth diameters, 383,000 kilometers, a quarter of a million miles, a 3 days journey to the moon. All right, so we now know everything about the moon today. We know its mass, we know its size, we know it's got craters all over the place. We've been there. 12 people have walked on the surface. We have rovers moving along the surface, investigating things. We have 800 pounds of moon rock. We know a lot about the moon. In fact, we have seismometers on the moon measuring moonquakes, which gives us information also about the inside of the moon and what the inside is. If you know its size and its mass, you know its density, and it's got a peculiar low density compared to the Earth. So its core, no one's ever been to the core of the moon, but we think on computer we can model the inside, and the core is much smaller than the Earth's core. We also know the distance to the moon very accurately because the Apollo astronauts left these mirrors, in which, and we know where these mirrors are located. They're still there, maybe covered by a little bit of dust, but they still use them, I think. Today, they send lasers up to the moon, and they can measure to within a centimeter or a fraction of a centimeter what the distance is to the mirrors by timing the laser beam back and forth. and it's about 1 light second up to the moon and back. And we now know that the moon is moving, it's drifting away from the Earth about a few centimeters a year, right? And so that's been going on for billions of years. That rate has gotten slower and slower as time goes on, but in the past it was a lot closer to the Earth. And we know that we can measure it today, but we can also calculate it. We can put it on a computer, and we can run the movie backward in time, and the moon gets closer and closer backwards in time. So here's the densities of things, the air that you're breathing. 1/1000th of the density of water, coal, diamond, iron, gold for comparison, shown here. And then you can compare that to the densities of the worlds. Earth is the most dense solid object in the solar system, 5.52 times that of water. The moon is made of Nerf compared to the Earth, right? So Nerf. So it's very fluffy compared to the Earth. Mars is also not very dense, and so we think its core is also smaller than that of the Venus and the Earth. So if you, this is the textbook today, the images showing the different sizes of the core. We call the Earth's core the core. It seemed when I grew up, when I was told this, the core is half the size. I was surprised when I was a graduate student to find out that the core is half the size of the planet. That's not the core. That's like the whole thing, or a significant fraction of the whole thing. So the mantle starts about halfway up. There's a fluid outer core for the Earth, and then you have this solid inner core. The fluid outer core, we think, is responsible for the Earth's magnetic field. The moon, by comparison, if you take its density and also model what we think is in there based on the way waves go through, and also how satellites move around the moon. The mantle makes up most of the moon. So the low density materials are almost all the way throughout. There's a small core, but there are people today who, this is a relatively recent image and a relatively recent press release this year. It's official. Scientists now know that the core is small. It's got a liquid metal outer core, just like the Earth, and a solid inner core. So maybe a little small magnetic field, but very, very small. It doesn't rotate fast enough, and it's not big enough. Anyway, when I was a graduate student, toward the end of my graduate career, let's see, that was 26 years ago, I was invited to write a chapter for this book. And so I don't know if you can even get this book these days, but there was a conference about the origin of the Earth and Moon. And that conference basically was a gathering of individuals to talk about one idea, one set of ideas in support of this idea that the moon was created when the Earth, when it was forming, was hit by something about this size compared to the globe here, right? So half the size, which is about the size of Mars, right? So when the Earth was forming, we think there was a collision, a giant collision. According to the ideas in this book, the giant impact hypothesis, which many of us, raise your head if you've heard of this hypothesis, right? So if you're interested in astronomy, or if you're paying attention in secondary school or college, they'll tell you about the giant impact model of the moon, which could be right. It could be right. But this was all that was there back when I submitted a chapter, contributed a chapter to this book. Anyway, the idea is that this thing hit the Earth 4.4 billion years ago, a glancing blow, and then it created a huge splash of material, out of which formed the moon. And all of those ideas, a lot of them were based on the Apollo program, which, you know, the ones to the surface, between 69 and 72, 6 missions to the surface, 2 people per mission, so 12 people have walked on the surface. And they returned 800 pounds of moon rock, which are still in the lab in mainly Houston, Texas. And what they do is they analyze the ages of these rocks, but also their chemical composition. And it points to a day when the moon was forming, when all the planets were forming. In the early solar system, there weren't just 9 planets or 8 planets or 4 big objects in the inner solar system. There were lots more. And the idea is that there were large numbers of small things, and then as time went on, they collided with each other, and then they got smaller and smaller numbers of bigger and bigger things. And then and the survivors are the ones that you see in the textbooks today: Mercury, Venus, Earth, Mars, and the moon, the survivors of that epoch. Now, this is a little misleading because, well, it looks like everything is all together, and maybe that's just for drama. There were collisions and stuff, but space is big, and so maybe there weren't as many big things in one small area. But notice how everything is molten. The other day, just last week, I think it was, there was a news item. There was an Indian rover placed at the south pole of the moon, and this was a Nature paper. And Nature is, it's really hard to get published in Nature, and they made a big news article about it. And I read it. What are they going to find out? They concluded that the moon was not only magma at the south pole or at the equator, it's also magma at the south pole, according to the results from this rover. And I thought, okay, so the whole moon was magma in the past. There's no theory, no matter what you come up with, there's no theory today for how the moon formed, which didn't involve the moon being completely magma with lava everywhere. Just like in this image, there's no way to have part of it be magma and part of it not. So I burst out to my poor wife. I said, look at this. They're getting all this press for, that's not news. The moon was magma. Anyway, 4.4 billion years ago, 4.4 billion are the nuclear or radiometric dates of the rocks that we get not only from the Apollo astronauts, but also from lunar meteorites. They get knocked off the moon, and they fall to the Earth, and they have the signature of other lunar rocks, and so they call them lunar tektites, I think. 4.4 billion years is the age of the oldest one, so we think that the moon solidified out of whatever the story is. It solidified 4.4 billion years ago, and so if you subscribe to the giant impact idea, then the impact must have taken place 4.4 billion years ago. We know meteorites that are older than that, slightly older than that, so the origin of the sun and the solar system probably occurred 4.5 or 4.6, close to 4.6 billion years ago. And so here's a recent...
On a time scale...
I'm trying to turn off. There it is. Okay, I want to turn off that
of a few hours?
No, I didn't.
On an enormous shock.
There we go. Okay, so there's a giant collision. Whatever direction this thing came in, that determined the final spin. Well, the original spin of the Earth as it moved around the sun. And whatever formed out of that debris formed in the equatorial plane of this object, and all of that was discussed at the conference that led to that book, The Origin of the Earth and Moon, that I had a chapter in, published in 1998, confirmation of a set of ideas to explain everything that we know about the moon. And so the idea of capturing the moon around the Earth, that was not discussed. That was thrown away a long time ago for reasons that I'll get into in a moment. And so it's very much been one-sided. The story has been one story, and it's in all the textbooks. The college textbooks are the same as now the web. Everything tells the same story, that there was this huge collision, and then out of that collision was born the moon in orbit around the Earth. Now, you'll see in this movie a lot of that material that was thrown up fell back to the Earth, because when you launch material away from the Earth today, if you do that, you put it into orbit. And it starts out at the Earth. If it's in orbit around the center of the Earth, it's going to fall back to the Earth eventually, unless there's something else going on, like other pressures, other forces, tidal forces, or some other gas pressures, explosions, which work outward. All right, so all of that has been analyzed over and over since 30, 40 years ago. And the conclusion is that if you look it up, geochemical constraints on the origin of the moon and the preservation of ancient terrestrial heterogeneities. This is 2020, and this is the textbook stuff about the moon. The moon is very similar to the Earth with two principal exceptions. The moon has a much smaller metal core, and the moon is more depleted in volatile and moderately volatile elements. For example, potassium, 1/6. If you take some crust and you analyze how much potassium is in the crust, if you do the same experiment with lunar material, it's less. It's about 1/6 that of the Earth potassium, and then sodium and zinc and chlorine also show deficiencies in the moon, which the explanation is that the formation of the moon involved a high energy, high temperature event, which those lighter materials that I just mentioned, potassium, sodium, zinc, those were vaporized and a lot of them lost from the cloud of debris. And so an impact is part of the story. And I'm here today to suggest that you preserve the impact, but you do it in a different way. You use it to explain something else. We'll do that in just a moment. The similarity of the Earth, you may have read, in major elements suggests that the two bodies formed from material from a similar reservoir. This is in all the textbooks, and I've been teaching about it for a long time. So those ideas on that last slide, remember those for what follows. But also there are papers today, people are doing the computer collisions over and over, and they find that if they do it in such a way that you don't need to form a debris disk, you can actually launch something the size of our moon and have it stay in orbit. There are other forces, gas pressures, which can actually suspend that object, that material, and have it be parked in orbit at the distance, maybe a few Earth radii, maybe 5 to 10 Earth radii around, and that thing then ends up being the moon. In other words, you don't need to have it accumulate from a debris disk around the moon. You can actually launch it immediately and have it form immediately. So depending on what computer program you have in front of you and what computer program you run, you get different scenarios. Some of these collisions produce more than one moon. Oftentimes what happens in those situations is the more than one moon, the multiple moons then collide with each other and merge. Some of them fall onto the Earth again. Some of them are lost into the solar system. So we don't get the same result every time. And so the story, even the giant impact story that everyone's been telling, it has variations to it. It's even more worrisome than that, as we'll see in just a moment. So the Earth and Moon are separated by a 3 days journey, 250,000 miles, and this is to scale. You can barely see it. I don't know if you can see it. The Earth is at the center. Let's zoom in. So the Moon, the collision and debris and the disk and stuff. The Moon, the collision was right there, and all the drama took place here. Right? It turns out that if you capture the Moon, that also has to take place there. Today, the Moon, there it is. I don't know if you can see it, but it's way out there, 250,000 miles away, 60 Earth radii away, really far away. It starts out here, so this is, whether you form it by capture or collision, it starts out here, and then tides, which are sometimes, it's easy to say and to imagine the waves and stuff coming in. Part of this story is the tides and how they operate in the Earth-Moon system and how they get the moon from here out to here. Again, today the tides are still operating, and they're moving the moon continually away from the Earth a few centimeters a year. All right, so the moon today, it's difficult to capture the moon. If you imagine it long ago, you know, most encounters are going to be like this. Objects come in, they have hyperbolic orbits, and they just have too much velocity, too much energy to capture just one object. This is the orbit of the, just for reference, this is the orbit of the moon today. And so the chances of a close encounter in which an object even gets that close to the Earth, that's really small. If it's a giant impact, there must have been an extremely close encounter. But if you, let's say that you took this object on that trajectory right there, if you bring it in, and let's say it loses somehow, it loses a little bit of energy. It slows down a little bit, and you have to do it, and you have to imagine how. Maybe there's another object in the way, maybe tides, I don't know. In order for tides to work, it has to be much closer to the Earth. Anyway, if that thing were to lose energy, a little bit of energy, then it could go into orbit somehow. And all these things were hypothesized and studied 50, 60 years ago. But the problem is, if the thing is captured, it's not a stable orbit. The reason why, look at the red. This is the orbit of the moon today. The sun is competing for the moon's attention there. So even the orbit of the moon today, it's slightly elliptical, and as the moon gets further and further from the Earth, the sun's influence is getting stronger and stronger. And so if you capture something and if you insert it into a temporary orbit, it's not a stable orbit. So this is an integrated, computer integrated orbit, and it's being pulled on by the sun, and it's only temporary. So in order to successfully capture something, it's got to be a lot closer where the drama took place a long time ago. So capture really has to take place where the impact and the disk of junk took place. It's got to be a lot closer. And you might say, well, I'm just going to throw my hands up, because what are the chances of it getting that close? Well, if we've been talking about impacts for over 40 years now, what are the chances of that compared to the chance of some other object getting slightly further away and being captured? And how does capture work anyway? You'll see in just a moment. So how do they make the moon? This is hard to read where you're sitting. It says there are three options here. This is the giant impact scenario. This is maybe you form the planet with a disk of stuff. How you produce the disk, no one knows. And then in this figure, which I found on the web, they're also including binary exchange. What in the world is binary exchange? So here you have the planet, and then you have a binary come in, and the binary, these two objects, and they don't have to be the same mass, M1, M2, and they're circling around, and it's a brilliant idea. I love how the physics of it, because it's relatively simple. So these two objects come in, and they're in orbit around each other, around the center of mass of these two, and one of them is traveling opposite the direction of the binary, right? So it's moving against the motion of the binary, and its velocity relative to the planet is slower than the velocity of the binary by the planet. So now if you can tidally pull these two apart, which the Earth does, if it's close enough, you pull them apart, one of them is moving opposite, this one's moving opposite this way, and it's traveling slower than this one's moving faster this way. So this is the one that's lost. This is the one which, if this velocity is below the escape velocity from the planet, it gets captured and stuck around, right? So it's kind of a fun idea, which can easily be modeled on a computer. So I wrote a simple computer code with this computer, right? So students come into my office all the time and they say, can I get involved in your research? And I'm like, your computer can do exactly what I'm doing. You know, it's just waiting for you to do this stuff. And really, it's just, for the students in the audience, it's just, you may have heard intro physics, F equals ma. You know, the forces on each of the masses give rise to accelerations. And I just have three masses here. I got the planet, and I got I have the sun off at some distance because the sun's important. And so you got the planet, you got the sun, and then you got this binary. The binary is coming in from below like this, and they're circling around each other. And then if the timing is right, a lot of the times it doesn't result in a capture, but in this case it does, so that's why I'm showing it to you. Right? And this is 5/1000ths of an Earth mass, which is smaller than the moon. There's the moon, 1% of an Earth mass. This M with a star donut, that's an Earth mass. So this is the size of the moon. This is a small thing, maybe half the mass of the moon. And this thing gets captured and it goes into this elliptical orbit. Again, most of these experiments on this computer ended up in no capture, but it wasn't that hard actually. Within 30 minutes, I found a capture, and then I tried different masses, and it's kind of fun. And so this tells you how fast the binary comes in relative to the planet. So you have to have a close encounter, 1.5 kilometers per second. That's 1,500 meters per second, or about 3,300 miles per hour. Those are typical interplanetary encounter velocities. And if it's slow enough, like those speeds, then you have enough time to pull apart the binary, and one of the objects gets lost and the other one gets gained as a moon. So then I animated it. So here it is. You got your binary flying around each other. And again, I could make the masses whatever, and I could start them out with whatever velocity. And this one was a failure. As you can see, they collide, right? So it's all about timing, and that one led to the capture. And the captured mass here is that of the moon. The escaping mass is a little bit less than the mass of Mercury, right? And then also, whether you capture or not depends on whether it comes in on the left or the right. So here it is coming in on the left, and we end up with a retrograde. So if this thing is going around the sun like this, then you can actually have this the satellite system, the binary, come in like this, and then you end up with a retrograde capture like Triton around Neptune. So the sun is off here. This is called the prograde. This is what our moon is doing today, right? So this object here is moving opposite the binary velocity, and that thing is captured, and this thing escapes. It turns out that this thing is actually quite slightly more stable and easier to capture than that one for interesting physics reasons. But just keep in mind that retrograde capture is a possibility. So here it is. Here's the example. They didn't separate. They ended up traveling off together like they were best friends and they couldn't be separated. All right, let's watch this again. So they come in on the left and they stick together, and that is because, if I go back, that is because if they rotate in the opposite direction, so if they're coming in on the left here, then they have to be rotating in the clockwise direction, the same direction as the binary is relative to the planet. And so in that way you can have a capture. You can also have this one rotating like this counterclockwise, in that direction, you can get capture. But you can't have it be the opposite direction because they do get separated temporarily, but they interfere with each other. The binaries interfere with each other if they're rotating in the wrong sense. So that is a counterclockwise retrograde fail. And this is a still image of what you just saw. These are moon-sized objects encountering the Earth. And then in this case, now I rotate them in the opposite sense, and you get one of them captured, like Triton around Neptune. But in this case, it's the moon around the Earth, or the moon, a moon-sized object around an Earth-sized planet. And then another object the size of the moon gets lost. Here's another example where you don't get a disruption and the binary just goes on its merry way. Again, it's all about timing. What are the chances then? That's a very good question, and everyone should be asking it. That's the next part of this project. What I've done and what I've written in this paper now opens up a whole new world, a whole new avenue of research, which I frankly, I'm looking up at the ceiling because I'm not sure that I have the time and the energy to do it all. And so if you're a developing student, you know, this is, if the scientific community embraces the idea and says this is worth studying, then there will be lots of modelers, and they'll play the video games, and they'll write the programs, and they'll see what's the probability of just the right outcome. All right, so could this apply to the Earth-Moon system? I started to ask after I found captures on the computer screen. I said, could the moon have formed this way? Well, first of all, how big of an object can you capture? This is a Mars-sized thing that is lost, and this is a Mercury-sized thing that is captured in it looks like almost a circular orbit. It's slightly elliptical. Mercury is 0.05. This is 0.04. Here's a 0.05. That is Mercury, right? So in the solar system, other planetary systems around other stars, maybe they have an Earth-sized planet with a Mercury-sized moon, you know, bigger than our moon. You know, if there was a binary exchange encounter. And here's another one, a Mercury-sized. This one, again, you launch a Mars-sized thing away from it. How do you form these binaries? I'm imagining this. And so is everyone else regarding Pluto. You've heard of Pluto. Pluto has a big moon, Charon. And those two were probably formed by collision. And so if you have two objects and they come together like this, and they lose a little bit of energy, and then they can tidally interact, and you can collisionally form the Pluto-Charon system. It is estimated that over 30% of the asteroids in the asteroid belt are binaries or triplets, collisionally formed. Or some of them actually were formed from a binary exchange encounter. People who study the asteroids, they not only observe these triple asteroid systems, binary systems, but also they see them in the Kuiper belt. And so a significant fraction of the binaries that I'm imagining are part of the Kuiper belt or the asteroid belt. In the early solar system, it's not out of the question that you had terrestrial planet-sized binaries, maybe with the Mercury in orbit around the Mars. And then if they had a close encounter with the Earth, then you can form huge terrestrial moons around them. Now, in this case, you lose a 0.04 Earth mass object, you gain 0.1. What is 0.1 again? That's the size of Mars. So given the right scenario, you could have a Mars-sized satellite around an Earth. That didn't happen in the solar system, maybe because it's unlikely. The other thing that's not going for it is if you follow what happens to the Mars over time, its orbit is huge because it's hard to slow it down, and the sun ends up pulling it away. So that is a temporary capture, and this it's at the mercy of the sun's pull. Anyway, here is, you've seen enough of these. So 0.03 Earth masses is lost. This one is a moon-sized mass, which is gained. There's the planet. Look how elliptical that capture orbit is. That's not the moon's orbit today. All right, so after I came up with these captures, well, okay, so could this apply to the Earth-Moon system? Now you need to do a tidal calculation. How do tides work on the Earth anyway? And now let's apply it to the Earth-Moon system, and let's put the moon temporarily in a highly elliptical orbit. All right, so today it's almost a circle, slightly elliptical, but what if we did this? What happens to the orbit when it's like this, and how do the tides compare to today? So just a reminder, an introduction to tides. The side of the Earth facing the moon is closer, so there's a high tide there. There's a high tide on the other side because it's further away from the moon than the center of the Earth, so it gets left behind. So there's 2 high tides a day, 2 low tides a day, so 6 hours between high and low. Right? And so as the moon goes around, it lifts the Earth's oceans. Now the Earth didn't need oceans for this to happen. Tides work with or without oceans. There are solid body tides. It works a little bit better if everything is molten a long time ago, right? So if there was a collision or if the thing was still cooling, then the surface can actually be lifted. The same thing is happening on Mars. And also the moon today, the surface is lifted by a few centimeters. So if you were standing there, you wouldn't feel it. Not like we see the water tides today, but even if it's a small amount, over billions of years, you can have significant astronomical changes. And so the tides that you're familiar with, Mount St. Michael, just off the coast of Normandy, France, it turns this tidal island into a estuary that you can actually get to, you can drive to or walk to. And also the most famous tides. How many have been there? The Bay of Fundy. We should do a field trip. Nova Scotia. It goes from high to low tide. Meters of water come in and out because of the undersea topography and the geography of it, right? So we get extreme cases of high and low tide. Now, it takes a little bit of time for the water to respond to the moon and then to flow and to build. So there's a little bit of a delay. And this is a technical slide. It's hard to see because it's busy. There's a little bit of a delay between when the moon is overhead and high tide. What do I mean a little bit? It's about 10 minutes on average. 10-minute delay. So there's a little bit of an angle between the high tide and the moon. Because the Earth is rotating faster than the moon is orbiting the Earth, that high tide is always ahead of the moon. And the moon lifts the tide, it forms the tide, and then that tide reacts back onto the moon and forces it ahead in its orbit. It's like a little rocket which accelerates the moon in its orbit and sends it forward. And that is responsible for the 2 or 3 centimeters of drift per year as it moves away from the Earth. That's been going on for billions of years. This dashed line is the point at which the moon would actually be orbiting faster than the Earth is rotating, in which case you would have the moon ahead of the tidal bulge on the Earth. In this case, you'd have an inward evolution. So if you're having a lunchtime conversation about the tides and the way they work, just keep in the back of your mind, it's complicated. Sometimes you get inward drift, sometimes you get outward drift, and it all has to do with whether the satellite is closer than this limit. This is the geosynchronous limit, or the limit at which you're orbiting once for every one time the planet is rotating. So geosynchronous satellites, they know exactly where to put the satellites above above the Earth. It's about between 5 and 6 Earth radii. And then they go around the planet once every 24 hours, right? So we can then point to the satellite, and it's always there, right? And so that's this limit here. Now the Earth was rotating a lot faster a long time ago, so that limit was a lot closer. And if the Moon was ever in this situation, it would have evolved inward. But today it's beyond it. It's well beyond. So it's moving out. All right. So tell yourself and your family and friends, tides can move moons, satellites inward or outward, depending on where the satellite is compared to this this distance called the co-rote distance or the geosynchronous distance. For Mars has 2 moons. You've heard of them, Phobos and Deimos, those asteroids. One of them, Phobos, is there compared to this dashed line. It's moving in compared to, and Mars doesn't have an ocean. It has its surface. It swells up and down, and so its tidal evolution is small. But Phobos is going in. Deimos is going out because it's further out, right? So in 10 million years or so, goodbye Phobos. It's going to hit Mars. All right, so that dashed line is where the planet spin rate is equal to the satellite orbit rate. Today the Moon is moving 2,000 miles an hour at 60 Earth radii. This is actually a real movie taken by a spacecraft beyond the Moon. And this is a complicated plot, but it shows how the distance to the Moon has evolved over billions of years. This is today. This is when it was formed, way back when. And the distance started out really close to the... So if you run the movie backward in time, it goes from 60 Earth radii today all the way down 20, 10, whatever it is. And the spin rate of the Earth has been slowing ever since. It started out with a few hour spin rate, and now it's up to 24. Right? Conservation of angular momentum, things you learn in physics class, and you wouldn't think to apply them to an interesting astronomical problem, but it's a lot of fun. So just to get back to the Earth and Moon capture of the Moon around the Earth, if you put it into a highly elliptical orbit, for most of the orbit, it's outside that red circle. So here's the geosynchronous circle. It's outside here. So this is all orbit expanding. All of this, if you take each point in the elliptical orbit, say orbit expand, orbit expand, orbit expand, orbit expand, now it dips within this distance here. So a long time ago, when it was closer than this red dashed line, the strength of the tides was millions of times. You can't read it, but this is this axis here. This is millions of times. It gets a pulse of tidal energy, which really slowed down the Moon's or accelerated the Moon's rotation and slowed down the Earth's rotation, and it caused the orbit to shrink. So this ellipse can be converted like this in very short time into a circle, right? The equations, not surprisingly, are ridiculous, the tidal equations, and they've been worked out long time ago, over 60 years ago by many authors, and we're all using the same silly equations. I'll show them to you in just a moment. There they are. The math up at the top. And this plot, this is eccentricity of the orbit. These green shapes are the shapes of the orbits at to different degrees. And so here's the circle down here. 0.6, this is what the shape of the orbit would look like. And this is close to 1 up in here. So if you start out the Moon on a captured orbit like this, there it is for these black lines. If we started out like 20 times the the radius of the Earth. If we started out there and if we solve these equations, we can actually get it to circularize and drift inward. So there it is. You can drift it all the way inward and become a circle. And then at that point, it crosses these red and blue lines, and that switches the direction of the tide. So it goes like this, and then once it circularizes, then on the plot, it reaches a new orbit expanding region, and then mathematically, then it starts to expand, but it expands in a circle. And that's what the moon has been doing ever since it was formed 4.4 billion years ago. It's been expanding, but in a circle, and it's been moving very slowly. I call that the long lunar drift. And this is what you have to have in order for it to agree with what we see today. Today it's way out here, and this begins the long lunar drift. I didn't integrate all that time because it would take billions of years of computer time, and I just said, okay, we're on our way. I've shown how you circularize it. So here it is. This is 1,000 years right there. So this is a tenth of a year. There's 1 year, 10 years, 100 years, 1,000 years. So in about 1,000 years, 10,000 years, the orbit eccentricity goes from 0.85-ish down to close to 0. And here's the shape of the orbit up there. And by the time you get down in here, 1 million years later, it looks like a circle. And here's the size of the orbit. It actually starts out, the size of the orbit gets smaller, close to the orbit of the Earth, and then it works its way out because the direction of the tides switches and goes in the opposite direction. When I produced these plots, it was a surprise to me how rapidly the thing circularized, and also it was surprising that it left me with the moon in the right place dynamically, which would then lead to what we see today dynamically with the moon at its present distance. The spin period of the moon would start out the same as the orbital period in the binary going in, and so it would actually accelerate and it would spin up. The moon through tides is spun up. Then it slows down, and this is where the moon's spin becomes captured. So today we see the same side of the moon every time we look at it. The spin has been captured, and here is the moment of capture. This is 10 to 100 years after capture, right? So that happens quickly because of the strength of the Earth's tide on the moon. And so the capture is there, and it's been captured ever since. And as it moves out away, the moon's captured spin, as it moves out away from the Earth, it increases its spin with the orbit. And the Earth, all of this happens at the expense of the Earth's rotation. So I started out with a 7-hour day, and then at the expense of the Earth's rotation, the Earth slows down a little bit. And then in 1 million years, it's up to 10 hours. In a few billion years, we're up to 24, which is what we have today. All right, so to conclude, the idea of capture was actually pursued vigorously back in the 1960s, and it was a viable theory. And everything changed when the Apollo astronauts went to the moon, and they brought back the moon rocks, and they were geochemically analyzed. And, right, so this is if you dig into it, it becomes confusing and convoluted in a hurry. Here's one such figure, and it's hard without a background in geoscience and geochemistry. It's hard to understand. But this is the ratio of heavy oxygen to another isotope of oxygen. So what the geochemists do is they analyze as best they can what the rocks are made of. And this line, you can see this line, they use this line as a reference line to compare the chemical makeup of the different rocks, the different types of oxygen isotopes. Anyway, the gray stuff, it says the moon. So this is the moon stuff. And then this is the Earth stuff from meteorites. And it says Earth and moon fall on a common fractionation line, indicating their origin from a single reservoir. This is what, this figure and others like it are why we've all been taught, and a student just said to me the other day in the office, Mr. Williams, I was told that the moon was made of the same stuff. He's quoting this plot and similar plots, right? So what you should ask then is, has this plot been remade? Are there newer, this was made a long time ago, but this was from a publication in 1996. Since 96, has there been newer studies? It turns out that there has been. Surprise, this 2020 paper, the Earth and Moon aren't made of exactly the same stuff. Distinct oxygen isotope compositions of the Earth and Moon. This is a 2020 paper, and it says, here we present high-precision oxygen isotope analyses and show that the Earth and Moon, in fact, have distinctly different oxygen isotope compositions. And our findings imply that the distinct oxygen isotope compositions of Theia, the object that might have hit the Earth a long time ago, and the Earth were not completely homogenized to the moon forming impact. In other words, they're keeping the moon forming impact. That is the storyline, and so they're trying to preserve it. Things weren't homogenized, thus providing quantitative evidence that Theia, the original Mars-sized thing, could have formed farther from the sun than the Earth did. And when I read that, I said, yes, it could have been formed further from the sun, and it could have formed in a different place altogether, and then been led to capture of the moon around the Earth. Let's go back to 1973, before the Apollo rocks were analyzed. This is a 73 paper. The integrations were performed backwards in time from the present day, and it was found that the lunar orbit rapidly becomes highly elliptical at the time of closest approach, thus indicating a probable capture of the moon by the Earth. 1973. However, it is shown that the detailed behavior of the system at the time of capture, in particular the inclination of the lunar orbit, which today is 5 degrees relative to the plane of the Earth's orbit around the sun, depends critically on the chosen rate of dissipation in the moon's interior. This paper and others like it talk about the possibility of capture, and they were completely forgotten by the planetary science community. Why? Again, because of the Apollo data and the geochemical analysis of the rocks. They said, no, this shows that Earth rock is equal to moon rock, and they must have formed out of the same stuff. What I'm encouraging the community to do is to go back and revisit these papers, but also to pay attention to the recent results, the recent geochemical results, and to ask, are they really that similar? And could the moon have formed somewhere else in the solar system and then come in with a binary and been captured? Here's some more lunacy. 1975, 1972. Here's a paper. Al Cameron, who's famous, has proposed formation of the moon inside of Mercury and the moon's subsequent